So far, I've been talking a lot about the merits of pilot wave theory. In this video, I'm going to discuss some of the weaknesses of pilot wave theory, and I'm only going to discuss them pretty briefly. So the first two that I have here are fairly related to each other, and this is underdetermination and ontology. So in general, underdetermination just means that our theories are underdetermined by the evidence. So there are multiple different theories that we could propose to explain the evidence. And this is not just a problem with Bohmian mechanics, but is something that's well known in the philosophy of science, period, that there are multiple ways to sort of fit something to the data. And so when we come up with, say, in general relativity, so Einstein's field equations for general relativity has a certain mathematical form that we interpret to be something like space-time is bending and flexing and curving and things like that. But then we come up with these ideas of it being something like a fabric of space-time. But the theory of a fabric of space-time is underdetermined by the evidence. The evidence that we get does not say conclusively that we have to interpret it as a fabric of space-time. What we mean by that is that the theory of a fabric of space-time is underdetermined by the evidence. And so in this case, what we have is two possible primitive entities, the particle and the wave. And so the theory that there is a particle and a wave is underdetermined by the evidence, because the evidence is something that can be predicted with just textbook quantum theory. And so proposing that we now have these two things, saying that we have to have two things similar to the fabric of space-time and general relativity, there is no way from the data that we have to say definitively that there must be these two things. Some of the problems with this is, what better predictions does this make? And this, again, is kind of a problem with all of the interpretations of quantum mechanics. Is like I've been sort of harping on quite a bit in these videos. The thing that a lot of these papers are trying to do is show that Bohmian mechanics can come up with the same predictions as standard textbook quantum theory, but does it make any better predictions? And that's going to be the way that you'd have to test whether the theory is actually true, or, at least closer to the truth. And so, again, proposing that we have these two possibly primitive entities is underdetermined because so far there hasn't really been, at least not that I've found, any sort of better predictions that are made by using the Bohmian mechanics interpretation over textbook quantum theories. And so if it does not make any predictions that are not made by textbook quantum theory, then why do we need this extra interpretation? And of course, things that I've talked about in previous videos is that there are merits to the theory. For instance, not having to have the collapse postulate is probably one of the biggest ones, where the collapse postulate is a huge problem in textbook quantum theory that we do not have if we subscribe to Bohmian mechanics. But if that's the only thing that it does, it's not really making any new predictions. And so when we propose these two possibly primitive entities here, we're not really gaining anything new from this. And so how can we account for the equilibrium hypothesis? So remember, this is a big part of Bohmian mechanics, is this quantum equilibrium hypothesis, which says that the probabilistic nature of the experiments that we do is more about our knowledge of the system rather than some sort of intrinsically probabilistic nature of the system. And so the quantum equilibrium hypothesis says that essentially every experiment will start with the particle in a position that is determined by the Born rule, so the square of our wave function. And so this is sort of an assumption here, is that that is true about where the initial position of the particle is. And so again, this is underdetermined because this is just sort of proposing this, but like I said here, it's taken as a given or a brute fact that the particles begin in positions that are described by the square of the wave function. So how and when did this come about? We can make this assumption, but why should we make this assumption? And so something else that I talked about briefly in the previous video are these empty waves. And so do the empty waves exist? There are actually some papers, and they were linked to in the lecture notes of my previous video, where people are trying to come up with certain predictions that you could make from empty waves. And so that is at least something that would help with this underdetermination by coming up with a prediction. If it is the case, if there are these empty waves and you make a prediction with it and your experiment shows that that prediction is true, then that would be a point in favor of our Bohmian mechanics, because that would be a better prediction, since the types of things that you would predict would happen with an empty wave is not something that you would actually see in any experiment that was predicted by textbook quantum theory. All right, so like I said, ontology, this is very related to what I was just talking about. We have this increased ontological complexity. So we have the particle and the wave rather than just this weird sort of wave particle thing. And so especially in philosophy, but also in science, we are always trying to sort of have the fewest things as possible, or the most, what they call, parsimonious ontology as possible. So you want the fewest number of sort of primitive or brute things in your ontology, because those are things that can't be explained. And so if you can't explain them, because you could just propose any number of unexplainable things in your ontology and then just, call it a day. But in science and in philosophy, you usually want to have the simplest ontology that you can possibly come up with. And so we are increasing our ontology here by saying that we have both the particle and the wave, rather than that they are both the same thing. Another question that I have, and this is probably not something that you'll find in a lot of other papers, because they might take the wave as just being sort of a brute fact, but my question is just, what even is the wave? So what is waving? I briefly discussed in a previous video that there is one interpretation of thinking of it as like a potential, and so this potential is sort of moving our particle around, but that then runs into some of its own problems. And so we don't actually know what is waving, why it behaves the way that it does. So if you look at like what this wave would look like, it looks very different than sort of the way that classical mechanics, where an object in motion tends to stay in motion and it doesn't change direction unless there's a force acting upon it. Whereas this wave seems to be sort of this thing that's constantly pushing this particle around in different directions without anything, at least classically, that we can think of would be actually doing this. And so this wave seems, I don't want to say arbitrary, because it can actually be predicted with the Schrodinger equation, but it just seems a lot stranger to me that you can have this constant sort of sloshing and moving around inside this wave. And so why does the wave behave the way it does? And so again, kind of going back to what I said earlier, what are empty waves? And that is just kind of getting at this thing that I was just talking about. If the waves are something that exists, and we can have empty waves, what is the empty wave? What is waving, and why is it behaving the way it does? Then there is also the problem, how does the wave interact with the particles? One of the things I've talked about before is the particles don't actually affect the evolution of the wave. And so this is a one-way interaction. So again, that kind of goes back to the Newtonian thing I was just talking about. If this wave is constantly pushing this particle around, but we don't have any sort of equal and opposite reaction of the particle to the wave, then we are thinking of something very ontologically different here between our particle and our wave. And so the other one is, how do particles decide which wave component it will follow? And so this goes to the sort of interpretation I was coming up with in the previous video about how entangled particles can sort of communicate with each other, and it has to do with deciding which component of the wave it's following. And so if that really is a good way of thinking about that, then how is it that the particles decide which component of the wave it will follow? This still, to me, seems like it's somewhat probabilistic. I mean, they even call it the collapse of the conditional wave function. And so if this interpretation of mine is correct, then it's sort of collapsing in the sense of deciding which component to follow. And then it kind of gets to that why did it decide to follow this one instead of another one? And that could probably go into the many worlds interpretation that it actually followed both of them, and we just so happen to find ourselves in the reality where it followed this one rather than that one. But that's something I will get to in future videos when I talk about the many worlds interpretation. Another issue here is non-locality. So it does not solve the problem of locality, but doubles down on it. Remember that the motion of the particle is dependent on the positions of all other particles in the universe, actually, really. So it's extremely non-local. Of course, this is something that a lot of people point to as being a problem for Bohmian mechanics, but Bell's inequality and subsequent experiments that sort of bear out Bell's inequality suggest that non-locality is inescapable, that it's actually part of any interpretation of quantum mechanics. And so this is not really a problem of Bohmian mechanics in particular. But if you are the kind of person who really subscribes to the universe having to be local, then this is going to be an issue for you, the inclusion of non-locality in the theory. And so the biggest one is probably this one. So when you read sources talking about the weakness of Bohmian mechanics, it's the non-relativistic aspect of it that's really going to get highlighted as a problem in Bohmian mechanics. And what this means is there is still no relativistic quantum field theory for Bohmian mechanics. Our Bohmian mechanics often requires what's called space-time foliation, and this means that there has to be a preferred frame of reference, and this violates Lorentz invariance. And so what I mean by space-time foliation is essentially this right here. If we have time going upward like this, we can sort of split space into these sheets like this. Obviously, in the actual universe, these would be 3D sheets here, but if we take it down to two spatial dimensions, we get these sheets here. And so if we are going to obey Lorentz invariance, then there are, I mean, really almost an infinite number of different sheets that you could put that would come through this point right here. You could have one that's very slanted all the way up to this 45-degree angle here for the speed of light. And then you could, of course, slant that in pretty much any orientation around this and at various different angles, and those would all be perfectly valid inertial frames of reference. But if we have this foliation here, this space-time foliation, we're saying that one of these ways of divvying out these sheets here is preferred. And so we therefore have to have a preferred frame of reference. There are, of course, attempts to try to make Bohmian mechanics relativistic. These are just a few papers right here, which are linked to in the lecture notes if you want to look at that. And so this is an ongoing thing here, trying to find a way to make it relativistic. You know, like I said, this is the thing that most people are going to point to as the biggest weakness in Bohmian mechanics. And so this is an active area of research. So a future version of myself is cutting in here real quick because I wanted to talk about another thing that is often levied against Bohmian mechanics, and that is that it has a classical bias, which means that it assumes that everything must behave classically and make intuitive sense to humans. And so, you know, saying that there is this definite particle with a definite position and everything is just showing that we have a classical bias, that we're not comfortable with sort of the strangeness of quantum mechanics. And so we are always trying to come up with a way to make it seem more like classical mechanics. So I think some of the issues I pointed out above, especially with ontology, indicates that Bohmian mechanics may actually not even be classically enough if we are committed to having a classical interpretation of quantum mechanics. However, the motivation behind proposing an actual particle as an actual position does attest to a classical bias. But yeah, anyway, I just wanted to interject here to say that this is also something that people point out with Bohmian mechanics. as a weakness, that it's something that people are just sort of proposing because we have this bias to want everything to seem more classical and intuitive to humans. All right, so just one last little comment here. Of course, some of these weaknesses, as I've pointed out above, are shared by other interpretations of quantum mechanics, and some of the weaknesses of those other interpretations are solved or explained by Bohmian mechanics. And by that I mean something like Bohmian mechanics does not require the collapse postulate of textbook quantum theory, which is one of the biggest glaring problems affecting textbook quantum theory. And so, like I said, there are definitely merits to Bohmian mechanics, but there are also some weaknesses to it. But as I said, a lot of these weaknesses aren't just for Bohmian mechanics, but for pretty much any quantum mechanical theory. But anyway, I hope you found this video helpful, and I will see you in the next one.
Whoa, 15 miles over the speed of light.
That's a violation of the law of Lorentz invariance, baby.
Light 'em up.
Look out for that particular individual.
An electric wall, eh? I can't see the harm in peeing on that.
Whoa, where my man learn that?
Sunny D commercial.
Let's refract this sucker.
DNA and career chip, please.
Erwin Schrödinger, huh? What's in the box, Schrödinger?
A cat, some poison, and a cesium atom.
The cat, is it alive or dead? Alive or dead?
Answer him, fool.
It's a superposition of both states until you open it and collapse the wave function.
Says you.
There's also a lot of drugs in there.